Hello, I'm Cherin Kim, the one of the PhD students in the VML. Today, I'll present the paper MoDi, Unconditional Motion Synthesis from Diverse Data. As inferred from the title and figure, this paper proposes an unconditional GAN method for the motion synthesis that generates various motion sequences from a latent space trained with a highly diverse and unstructured motion dataset. The motion synthesis is a method of reusing the motion data to generate natural motions like this that satisfy given cues or spatial temporal constraints. Naively interpolating between two motions or blending them can be used. And with the growth of neural network methods, many neural models for the motion synthesis have been developed in recent years. However, most of them focus on action condition generation. PFNN needs space labels for the motion data, and ACRNN is conditioned by a set of initial frames. And the actor requires a structured data set and is conditioned by a label indicating a specific action. So the authors propose MoDi, an unconditional generative model trained on completely unsupervised setting from an extremely diverse, unstructured, and unlabeled motion dataset. Given the Gaussian noise, the model generates various and natural human motion sequences like this. The basic concept is simple. They utilize the StarGAN2 network for the motion domain. The network structure is same as the StarGAN2, but it is difficult to apply the naive StarGAN to the motion domain because there is a domain gap between the image and motion. The image possesses a regularized 2D spatial structure with a relatively large number of degree of freedom, while the motion data is irregular, consisting of a skeletal graph with a temporal axis that has smaller number of degree of freedom. Therefore, they developed 3D skeleton-aware convolutions based on the skeletal convolution represented in Aberman in 2020. As I mentioned, same as the StarGAN, the network receives a noise vector drawn from Gaussian distribution and outputs a natural and temporal coherent human motion sequence. This generative model consists of two networks. First one is mapping network, which learns to map the Gaussian distribution into a latent distribution that corresponds to the distribution of the training data. Note that each point in the latent space represents a sequence of poses. And second one is motion synthesis network, which learns to convert a learnable constant tensor into a motion representation via a series of 3D skeleton-aware convolutional and unpooling layers. The intermediate layers are modulated by the star codes from the latent space. And before the detailed motion model structure, let's see how the motion is represented. The motion is represented by temporal coherent 3D joint rotations, and P is the number of frames, and J is the number of joints, and the K is the number of rotation features. And for the final motion outputs, they use unit cotillions. In addition, there are two more components. The authors extract a sequence of 3D global displacements of the root root joint for the character's position, and the binary foot contact labels in order to the network to learn for refrain the foot sliding artifacts. And for the root positions P and foot contact labels F, they geopad the feature dimensions of them to the size of the rotation feature K, which makes all joint entities possess the same number of rotation features. Then they concatenate them and obtain the full motion space M. Here, E is the J plus 3, which is the number of entities. Returning to the network architecture, as I mentioned, this model networks the same as the Daejeon 2. The Gaussian noise vector G is passed through the several linear layers of the mapping network and is converted to the latent vector W. In the motion synthesis network, given latent code W, the stellar vector S is obtained by applying Lund-affine transformation. And in each module, the modulation and demodulation are performed on the convolutional weights with the style code S. Then this styled weight is used for transpose convolution of the layer features. And here they use skeletal convolutions instead of the normal convolutions. To generate a fine character motion starting from the coarse skeleton template, they adopt the concept of skeleton convolution and pulling from the represented in the Aberman. And previous work used 2D or 1D skeleton convolutions where they combine the joints and the rotations into the same dimension. And the skeleton pooling is done by simply averaging the features of two entities. And to inject this style code to each rotation feature, which is called channel, separately, the authors proposed a 3D version of the skeletal convolutional filter and replaced the skeletal pooling by this. And each entity in the coarse character sees only weights related to relevant entities of the fine character, represented by the saturated colors like these in the feature like this. So the left arm is convolution with this part and this part, and other parts are ignored. So converted like this.
So here L represents the level of pooling.
Yeah, the hierarchical level of the network layers.
Okay, can you explain that?
Here?
No. Yes. Yeah. So in the current slide, can you explain again? Yeah. Here, L+1 goes in the depth direction, and then L is in the height direction. So how is it constructed again?
The E is the joint axis. So the EL+1 is fine characters of the joint axis of the fine characters, and EL is the coarse characters of the joint axis of the coarse characters.
And then what is the U again?
U is the I didn't mention it in this slide. The U is the filter width, and they are not they didn't mention how to set the U, and I think the U is the manual parameter.
Manual parameter?
Yeah, I think.
Okay, so you apply the pooling in different levels, right? So whenever you apply pooling, you construct this structure.
And the next slide is the how to
Okay.
apply these
Okay.
features.
All right.
And let's take a closer look at how this filter works with the downsampling example. The A is data at hierarchical level L, and its dimensions are KL times EL times and TL. And for the visualization, we omit the channels of K. So we see the figure in E and T. And to perform 3D convolutions, the data is padded by zeros like P with the EL minus 1, EL minus 1. And then the filter slides along the TL and EL axis of the data block, and then D is generated. Finally, the KL plus 1 number of D comes out as an output of the one skeleton aware neural model. Okay. And in addition to the generator, they also use a discriminator to generate realistic motions. And it has a reverse architecture of the synthesis network. It receives generated or real motion and processes it in skeleton or neural blocks that downscale gradually. And the generator and discriminator losses are as follows. Like other GAN models, for both generator and discriminator, they use a non-saturating adversarial loss like this. And the L touch and F con is in the generator loss is for the foot contact. There is already special care for foot contact in the adversarial loss, as M contains foot contact labels, but they noticed that encouraging the foot contact additionally improves the naturalness of the motion. So the L touch is encouraging regulations for the foot contact labels. And LFCon is the contact consistence loss, which requires that a high velocity should not be possible while a foot is touching on the ground. And for more detail, please refer these the previous papers. And in their experiments, they set lambda touch to 0.01, and the lambda fcon is 1, fcon to 1. And although these losses mitigate sliding artifacts, the authors also used standard IK method from Ganymeter to further clean foot contact. And as same as this diagram too, they activate regularization terms in a lazy fashion. And the main losses are computed every iteration, but these two losses are computed once for every 16 iterations to reduce the computation cost. And the LPass is the LPass is the path length regularization for good conditioning in the mapping from latent codes to motions by encouraging that a fixed size step in the latent space W results in a fixed magnitude change in the generated motion. And the LR1 is the R1 regularization for the discriminator to improve the functioning of the discriminator. And for more detailed explanation of these two terms, please refer the paper slide right below. In results, they use 64 frames for T and 20 joins for J, and they use Mixamo data, and which consists of approximately 2,500 diverse motions applied on 70 characters, and the running environment as follows. And they did lots of experiments, and I will show you in this presentation, I will show you several visual results of them. And they demonstrate that the latent code W is well structured by clustering it into meaningful collections of motions with 8 clusters using k-means. And its latent codes represent a whole motion sequence. The clusters represent semantic groups of the data, such as the green ones show sitting motion, and the purple one shows like dancing motion.
Did you say this clustering is automatically happening in the latent space, or they additionally apply k-means clustering here?
The latent code is well disentangled, and they show how they disentangle. So
this clustering is automatically formed in the latent space.
Yeah, and they're using the k-means clustering with for the visualization.
For the visualization.
Yeah. The latent code is well disentangled. And well structured.
For the visualization, they apply k-means clustering. K-means clustering means they additionally do the clustering.
Yeah,
if it's already clustered, why would they additionally apply k-means clustering?
I think they use k-means clustering for the visualize the latent clusters. I think. Not for the results of the motion. How can I say?
In my opinion, the latent space isn't really labeled. So you project all the dots here using the mapping network. And then from those like data points, they just compute the k-means algorithm to cluster the groups and see whether the group actually represents some kind of meaningful motion. And they're trying to say that for each group representation, the motion is similar. So I guess this doesn't really show, the method doesn't really label what latent code it actually means, but they found that it's kind of well disentangled in general using k-means cluster.
Can you say that again? I didn't quite understand. So they additionally applied k-means clustering.
So after training, you'll have a good latent space that is trained on this motion data set, right? And then from this latent space, in the latent space, you will have many points, right? You just cluster that point using k-means, and then see whether that group or the cluster points represent some meaningful motion. And I think that's what they're showing here in this figure. So for example, in the red dots in the left upper part, you can see the motion is like walking. And on the other side, in the green dots on the bottom right, you can see the motion, the motion is like sitting down or laying down in the in the latent space. So from that, they're trying to say that the latent space is somewhat disentangled and represents some meaningful continuous motion here.
Yeah, okay, that makes sense. Yes. So do the verification, they do the image clustering and then do the visualization to see it actually correctly entangled. Yes.
Okay, thank you for explanation. And I will run another visuals. And they demonstrate the linearity of the latent space by interpolating between the latent value. Here, the middle motion is still sitting motion, similar to motion 1, but it is also changed toward the semantics of the motion 2, like raising hand. And MoDi can take a motion sequence that was not seen by the network during training and find the point in the latent space that can generate that motion. And by optimizing their inversion module to compare the difference between the original motion and the generated motion, they can find where the original motion is mapped in their latent space W. And Shen et al. Showed that the disentangled latent space contains direction vectors that consistently correspond to individual vectors of variation. And taking their method, MoDi can get the added motion with semantic attributes like raising hands. And compared to the naive editing of joint rotations, MoDi can generate more natural hand raising motion like this. And the author also showed that MoDi can synthesize more natural motions compared to previous works in the same setting. As you can see, this is the actor's visuals. And the MoDi's visual is like this. More dynamic and more natural motions. And in summary, the authors describe MoDi's contributions as follows. The MoDi can synthesize diverse natural motions in unconditional manner using StarGAN. And to apply this StarGAN to the motion domain, they proposed a novel 3D convolutional filter that replaces skeleton-aware plea. And in their results, they show many applications, even for an inversion mechanism from real motions to the latent space. And in the paper, the authors mentioned two limitations as follows. First, the quality of the generalization power of MoDi is a direct function of the training data, which is still lacking at least compared to image datasets. The second one is the large running time for the skeleton-aware kernels with dedicated kernels per joint and large volumes. And they represent the future work like learning motion priors from the videos. And this is the end of my presentation. And thank you for listening. And any questions, comments?
Thanks a lot for your great presentation. And the general idea of this paper that I really like, they took the StyleGAN and they adapted to the motion domain. And the very good idea behind that is using the convolutional layers that are designed for a skeleton. So my question was that, did also people try to use diffusion models in motion domain? I mean, one can exactly do the similar thing by taking the diffusion models that are producing very realistic images in the image domain and somehow adapt the motion domain to them, similar to this work. And if someone did not do that in the past, it can be very cool because now diffusion models sometimes have very better results. Have you ever seen a paper that used diffusion models in motion domain?
That is the good comments for the research on the motion. And I didn't read many papers for the diffusion models, so I checked it later. And thank you for your comments.
Thank you so much.
There are actually some paper that does diffusion in motion. I think
Mm.
there's like 4 or 5 right now out there that is recently published. Not published, but archived.
I also, should I just, okay. I have a question about the, since this is using the style structure to generate the motion in unconditional way, and I wonder if it's like, if there's a similar method that generates just a single pose from unconditional generative network, and I wonder if it's better to generate the motion. I mean, is there a, how should I say, significant difference between generating the pose or generating the motion? Like, you know what I'm saying?
I didn't know the generating generating one pose in unconditional manner, but
So I was asking this because, for the pose estimation from 2D image, there are kind of two ways, like for video to 3D motion estimation, there are methods that tries to estimate the 3D pose from every single frame and then merge it to make a full motion data. Or there's another method that tries to directly generate the motion from the video itself. So I wonder if there's kind of trade-off or some kind of benefit for generating the motion directly or generating the pose for single poses and then somehow merge or combine it into motion. Would there be any some kind of, yeah, you know what I'm saying?
I understand, but it is hard to explain in English. And if you combine the generated pose, each pose, then it is okay, but there can be the like not smooth the motion which is combined with each poses can be not smooth.
Like it may contain some kind of jittering or something.
Yeah, or popping. And so yeah, I think.
But like when we think of 2D style structure, we can do the latent space interpolation. And when we interpolate from A to B, it kind of goes very smoothly, like yeah. So I wonder if we train a network that generates a pose similar to this style structure and make some kind of interpolation between the latent space vector to vector, then would that also make kind of smooth motion?
And the interpolation is not very well to the it makes the smooth motion, but it can be unnatural motion, like too smooth. I think how can I say?
I think the question Xian actually asked in the first place was about the problem definition. So it's something like you said, you can give a pose and then generate motions. Those things are like future prediction in video. Let's suppose you have an image and what will happen in the future is like future prediction. And I guess in this case, it's just trying to generate random motions. And I guess if you're trying to like interpolate two latent closing here, it's somewhat like blending two motions. If you think about it. So let's suppose you're having a jumping motion and a local motion, AB, and then you're trying to interpolate that. Then I guess I'm not sure whether it would naturally give a smooth motion, but it might give something that might be temporally smooth. However, I think just posing this problem as a pose generation might not actually do the work, because generating motion, you need the trajectory to generate the actual good motion. But if you just interpolating one pose to another, you're just trying to change the pose one to another. It might not be a motion, it just be a simple interpolation. So I think the problem is, how can you find if you're training a generative model using poses, in order to make motion, the problem will be, how are you going to find the natural motion trajectory in the latent space such that you would have a natural motion in the end.
I think I got the point. Since you don't know the dynamics of how the motion will gonna change or goes on, or the speed or some kind of other things, it would not be just enough for interpolating between one vector to another vector in latent space.
And the generating just the pose, not that window can be can have like detailed pose, but in the positive way it can be detailed, but in negative way it can be like noisy or copy pose can be generated. But when you generate the motion sequence that can handle the temporal information into noise function. So yeah, the difference between motion synthesis or pose synthesis is temporal information is included in the output motion.
Any other questions?
I had a question.
Can I have 1 minute? I mean, since we are running out of time, can we do it later and personally?
Okay.
Because we have a full side
Mm.
presentation, which will be very long. Okay, I'm
Okay.
sorry.
Okay, then I finished my presentation. Thanks for listening.